Ankara. I'm currently with the British University in Egypt, and I am a professor of information systems at Ain Shams University. I'm on secondment right now. I have an undergraduate degree from the University of Alexandria Engineering in telecommunications and electrophysics. And then I have my master's degree and my doctorate degree from North Carolina State University in computer engineering. And now I work in different issues or different topics, basically knowledge discovery, and my passion, which is computer architecture and specifically interconnection networks. So the topic is advances in interconnection networks design, pruning hypercubic networks. I'm going to define interconnection networks and then talk about two specific types, which are the generalized hypercube and the binary hypercube, and then how we can improve or modify some of their characteristics and connectivities and why we're doing this. And then we'll see if that has some elements of success, hopefully. Now, what are interconnection networks? They're key components of parallel systems, networks on chips, data center switches. They are the graph. Basically, I'm going to talk about the graph which the network follows. And nowadays, of course, they are employed to connect cores, processors to memories or computers. So the role of interconnection networks has expanded manifold. Actually, a long time ago, they were used in voice switches in public exchanges. And then these types of connectivities or graphs were used to connect computers to computers and then processors to processors or processors to memories. And of course now, it's on-chip networks. In addition to that's at a small scale, at a larger scale, it's data center interconnects. And one major topology for such networks is the generalized hypercube. Such an example of an interconnection network can be just a simple ring network or a fully connected network. This is what a generalized hypercube, for example, would look like. This is a small graph. We have 9 nodes, and it's 3 by 3. And then the connectivity is as you would see. So every node would represent a processor. Why would we need this? Of course, for any kind of parallel machine at chip level or at system level or a data center level. So this is the generalized hypercube. Why is this specific? It's a very generic and large, it encompasses a large family of graphs. If you notice here, these are 2-dimensional. We have 2 dimensions and we have 2 digits representing each processor. And in every dimension, there's a fully connected graph. So we'd say in this dimension, for example, we have 3 nodes and each node is connected to the other 2. This same node has another dimension here, which has 3 nodes, and again, it's fully connected in this dimension. So now, why is this important? Because the distance from any node, the distance, if you want to go from this node to this node, you can just hop to this node and then this one. So the maximum distance is the number of dimensions we have, which is 2. If we take another look at another generalized hypercube, this is a representation of a 3-dimensional graph. And we have 2 by 4 by 3. So 2 by 4 is 8, by 3 is 24 nodes. Now, the number of dimensions here is 3. This is 1 dimension, this is another dimension, and then this is a 3rd dimension, X, Y, and Z. Now, in every dimension, it's fully connected. What's the maximum distance this message needs to travel? 3, because we have 3 dimensions. So, for example, if I want to go from this node to the furthest node here, I would have multiple paths, but they're all the maximum distance are 3. 1, 2, and then 3. What's wrong with this graph? It's great, it's small distances. I can use it to map a lot of algorithms, matrix multiplication, sorting, image processing. I can map the data to these processors, and then I can design a parallel algorithm that optimizes or tries to optimize the performance. So the definition of a generalized hypercube is a network of of d dimensions, contains n nodes, can be factored into this multi-radix or multi-digits or multi-bits. I don't want to use the word bits because these are different radixes or radices. So, and then we connect each two nodes if there's a distance, a Hamming distance of 1 between one node and the other, then we can do the connection. So 2, 0 and 2, 1, there's a difference in 1 digit, so that we connect these two. But 2, 0 and 1, 1, there's a difference of 2 digits, so we do not connect them. Again, here, there are 3 digits for an address, different radix. In this dimension, there's 0 and there's 0 and 1. In the second dimension, this is 2 and then 0. So only one dimension is changing. This is the first. And then you can apply this to all the others. It's simple routing. Every processor has its address, and then the routing becomes as easy as 1, 2, 3. These are some characteristics of this graph. The degree, diameter, these are the two main characteristics or parameters. The degree is number of links per node, and this is important because it represents the number of I/O ports per processor. And then the diameter is the maximum distance from one node to the other, the maximum distance among the set of shortest distances. Why is this important? This represents communications overhead in a small network. This is part of the communications overhead, how far the message will travel. And the degree, of course, represents the complexity of the communication inside one node or inside one processor. There's the average distance, of course, and then there's the average message traffic density, which is, to simplify matters, defined as the average message distance multiplied by number of nodes over the total number of links. This approximates how many paths go through each link, actually. Now, what's the problem with this? Too many I/O ports here. Too many I/O ports, too many links. So we tried, the concept of pruning is trying to remove the links without affecting the characteristics of the graph, without affecting how different algorithms such as matrix multiplication is mapped to the graph. We can also implement the generalized hypercube or any graph as a multi-stage network, which means that these are switches, and then we can, switch from one node to the other. These can be processors, these can be memories or processors and processors. So it's just connectivity between whatever you choose. And these are switches. But what I work on are static networks, so no switches here. That's another type of implementation of the hypercube, is bus-based. Just like, these are buses for to transfer the data. And then these processors are hooked up to different buses so that we can guarantee that there's a path from one processor to another, to any other, in a minimum number of hops from one bus to the other. All this can happen now inside on-chip, and the implementation can be many technologies. Our concern now, or the future, of course, the present and the future, is optical implementation through optical devices, fiber, and so on. The simplest generalized hypercube is called the binary hypercube. And it is simpler because it is to the base 2. So the binary hypercube has just a uniform radix or base that is equal to 2. And everything in it is proportional or related to log to the base 2 of n. which is the number of dimensions. So everything happens in log n, which is of course very much desirable than to have a ring network, which all the communication is in order of n, or fully connected where the complexity of the processor is order of n squared. So this is log n. This is a great suggestion for a network. It has been used for years, but again, what we're trying to do is to avoid using a lot of links and removing links without affecting the performance of the network as much as we can. So for example, this is a hypercube of size 16. We systematically remove some of the links, and we have what we call the thin hypercube of size 16. And I'll be talking about an interesting characteristic of this pruned graph right away. This is the construction of the hypercube, the thin hypercube. It's a small, short algorithm that defines who's connected to whom in the processes. So very straightforward. And then we get half the links removed. I mean, for the black nodes, for example, they should be connected horizontally and vertically, but we've removed the vertical links. And for the white nodes, we've removed the horizontal links and kept the vertical links. Now, this is a removal of most or half actually of the links of this graph. The interesting thing, we maintain one important characteristic, which is the maximum distance inside the network. So that's the maximum allowable delay, the maximum delay we can have, for example, from this node, from this black node to this black node. So this is size 64, so it is 2 to the power 6. So the distance would be 6 from maximum distance of 6 from one to the other. And that's with the removal of half the links, systematic removal of half the links. This is quite something, because when we talk of VLSI implementation or optical implementation, the complexity of the implementation is reduced. Of course, there's a price to pay with regards to the amount of traffic that passes through every link. So the thin hypercube, the diameter of a thin hypercube size n, and number of dimensions n is log, which is log of n is n, and the degree of node is halved. That's the number of links per node, and that's quite an achievement there. I did this proof, I have the proof, of course, but I did it some time ago, and I decided to see if this will apply to the generalized hypercube, and we prune or remove links from the general hypercube. I would call it the reduced cube or the red cube. And I did apply an algorithm for this reduction instead of applying it to binary addresses only. It's just multiple red. Any kind of address with multiple. I mean, instead of X being binary all and Y being binary all, this can be to the radix 3, 4, 8, 9, whatever. And so we have a general hypercube, and we did some. This is the construction algorithm of the red cube, and this is a pruned generalized hypercube of size 27. Now, with the binary hypercube, I have to have multiples of 2. With the general hypercube, I can have any size we need, not necessarily multiple of anything. We've removed half the links again, and we have. Now, the question becomes, did we maintain the main characteristic of the maximum distance? So this is the degree. The degree has almost been halved. Again, the degree is the number of links per node or number of I/O ports per processor. This is size 256. The complexity is clear. I have a routing algorithm which takes me from it's self-routing. You know one address and the other, and you can immediately identify which path to go through. Now, there are two theorems which we prove: the diameter or the maximum distance of a red cube of size n, the number of dimensions n, which is the number of dimensions we have, has an upper limit of n plus 1. So the point is we've halved the number of links in the graph, but we've maintained the diameter to n plus 1, which is 1 more than what it was. But we've also discovered something, that's theorem 2. If we have one of the dimensions binary, that's 0, 1, then we can maintain the dimension, the diameter to n. So either n plus 1 or n. We've done some comparisons with respect of number of links or degree of node. This is generalized hypercube. This is the hypercube. This is the reduced cube. And this is the thin hypercubes. So the degree of node, that's the number of links per node, has gone down, as you see in the graph in front of you. And this is log 2 of n. So for example, this would be 2 to the power 10. That's 1k nodes. And we'd have these number of I/O ports within every processor. So that's for 1,000 processors, we'd have, for example, 6 ports per processor here or 15 here. So that's quite a reduction in the number of links or ports used. And the diameter, we've got some good results. Of course, this is the one with the most links, and then this one, and then these. And of course, the diameter, we pay a price that the distances increase according to the type of network you have. But for the hypercube and the thin hypercube, for example, whether you use a lot of links or a low number of links, you still have the same distances. And that's quite something. Again, for the generalized hypercube and the red cube, we've removed the nodes from this one to get the red cube, and we only have slight increase +1 in the number of the distances. This is the cost, which is just the diameter multiplied by the degree. That's to balance both parameters. And it is possible, this is my conclusion, and and where I ask for cooperation actually, and they identify the areas where I need cooperation if you are kind enough. So it is possible to maintain the low distances and virtually the diameter while removing almost half the links of a generalized hypercube. And then there are specific subclasses where the diameter can be maintained. And then the comparisons with other major interconnection networks show the advantage of the red cube in terms of diameter, degree of node, and cost. Now remember, these are graphs. We need to take them to the real world. We need to study how they can be implemented on chips or their VLSI layouts and characteristics, bisection width, symmetry, routing, fault tolerance capabilities. And then specifically, I'm interested in the implementation through optical technologies. And this one is more interesting to computer scientists like your kind selves, the efficiency of mapping algorithms and computations in terms of mathematical complexity, because we need to distribute the data, we need to write the parallel algorithms, and we need to see how their complexity will be.